Okay, so we are following up on a video that I recorded about numerical integration, basically finding the area underneath a mathematical curve. If you've taken Calc 1 and Calc 2, you know this is an important thing that we do in mathematics. If you haven't, you might not know why this is an important thing to do in mathematics, but surely you can understand the question. You've got a mathematical function and you want to know what is the area in square units of x and y underneath that curve. And in the video, I described a way to approximate that area by just dividing it up into rectangles. And as you make those rectangles smaller and smaller and smaller, narrower and narrower, the area of those rectangles, if you add them up, is close to the area under that curve that has a smooth top instead of sort of this stair step top of the rectangles. And the more you divide that the more you divide that interval into smaller and smaller and smaller pieces, the closer that that correspondence should be, the closer that approximation should be to the true area under the curve. I've got an old program here in my thing, so I'm going to reload that, and we'll start from scratch here. So I've got a program that doesn't do anything yet. I create my new scanner object so I can ask the user how many divisions to divide my interval up into, and prompt the user for that number, and I'm going to create a variable. It's going to be a double, not a float. I'm just going to pretend that floats don't exist probably for the rest of the semester. We'll just do doubles for everything. There's no real good reason not to if we're not trying to save memory. We're going to read from the scanner the next double, and we're going to call that divisions. So divisions is going to be the number of intervals we chop our interval from 0 to 1 into. And we're just going to do this for the function y equals x squared from the interval 0 to 1. We can make it more general. We can make it work for any function. We can make it work for any interval from 0 to whatever, or from a to b, where a and b could be any two integers. For now, let's just do it from 0 to 1 of the function y equals x squared. Let's make our lives as simple as possible. So we're going to need some variables to describe our mathematical calculation here. What are they going to need to be? I'm going to need the xy coordinates of my points on the curve. So I'm going to create a double called x and a double called y. And those are just the points along the curve. I'm going to need a number that's the width of the divisions. So I'm going to call that, I don't think I can put a delta in for a variable name, so I'm going to just call it dx. Those of you who have taken calculus should be entirely comfortable with calling the width of that interval dx that we're going to make very, very small. And then I'm going to need the area as I add up all these little rectangles to get the total area. That running total, we'll call it area. We'll go ahead and we'll initialize that to 0 before we add anything up. So now we need to think about an algorithm for what we're doing here. What are we doing here? We're dividing the interval into a number of divisions, and then we're calculating the area of a rectangle from 0 up to that function. So our x coordinates of our edges of our rectangles are going to be 0. Say we divide it into 3 pieces, right? Our coordinates are going to be 0, 1/3, 2/3, and 3/3. If we divide it into 5 pieces, it's going to be 0, 1/5, 2/5, 3/5, 4/5, 5/5. So our x coordinate is going to go from 1 over the number of divisions up to 1. And that means each rectangle will have a width of just 1 over the number of divisions, right? If we divide our interval from 0 to 1 into 3 pieces, each rectangle has a width of 1/3. So I've got some comments to that effect here that I'm just going to copy and paste over. So our x coordinates will be 1 over the number of divisions, 2 over the number of divisions, all the way up to the number of divisions. And each of our rectangles will have a width of dx, where dx is just 1 over the number of divisions. So that's our x coordinates. What about our y coordinate? Well, our y coordinate is the point on the curve, right? So if our function is y equals x squared, the y coordinate will just be x squared. And then the area of our rectangle will be that y coordinate times dx, times the width of our little rectangle. And again, this was all explained conceptually, mathematically, in the previous video, this is just turning that into code. So we're going to have a loop to add up all these rectangles, and that loop is going to be for, and I'm just going to call each rectangle, I'm just going to use the variable rectangle. So we're going to have rectangle 1, rectangle 2, rectangle 3, all the way up to rectangle, the number of divisions that we have. So for rectangle equals 1 to the number of divisions, right, 1, 2, 3, 4, 5, up to how many rectangles we divided up to, we're going to make the rectangle 1 bigger every time. Let's end our loop here so we don't forget our closed bracket. We're going to need the x-coordinates for each of our points along the x-axis. So those are going to be what rectangle we're on, 1, 2, 3, 4, 5, divided by the number of divisions. So again, if we're dividing into 3 pieces, our x-coordinates are going to be 1/3, 2/3, 3/3, right? Rectangle 1, rectangle 2, rectangle 3, divided by the number of divisions. And then our dx, the width of each rectangle, is just going to be 1 divided by the number of divisions. I'm going to make this 1.0 just so I don't get a integer versus double mismatch error. I don't think I will, but no reason not to. I want to cut those errors off at the pass if you can. If you know you're going to be dividing by a double, by a decimal, just make your 1 a decimal also. And then my y-coordinate, the other corner of my rectangle, is just going to be x squared because that's my function. Y equals x squared. It's a parabola. It would be whatever if our function was y equals sine of x, this would be sine of x. If our function was y equals e to the x, this would be e to the x. Whatever our function is. So it's x squared. Rather than using the math library, the power method, I'm just going to use x times x. It's an easy way to square something. Then what is the area of each of our little rectangles? The area of our rectangle is dx, the width of that rectangle, times the y-coordinate. But we have to add that to all the area we've calculated so far. So for each rectangle, we add the area of the current rectangle, which is dx times y, to the current, the running total of area, the sum of areas we've added up so far. And then we can end our for loop. So that should do it. That should add up all the areas of all the little rectangles, 1, 2, 3, 4, 5, up to the number of divisions. The horizontal size of that rectangle is just 1 over the number of divisions. The vertical size is just our function. In this case, y equals x squared. And then I just need to print out the output. So I'm going to have an output statement that says, out here somewhere, let's get rid of some of that. Oops. Paste. Fix my indentation, make it prettier. Java doesn't care, but I care. I don't want my program to look terrible. The computed area of the rectangles is, and then just the area variable that I've calculated. Okay, so that should do it. Let's go ahead and run it and see if it works. See if I have missed any semicolons or anything. See if I have any errors. I don't think so. Only one way to find out. Code HS is blinking at me. Good. So no compile time errors. Let's go ahead and run it. So the computer asks, how many segments should I divide the interval from 0 to 1 into? In our example, we just divided into 3. Let's say 3 and see what it says. The computed area of the rectangles is 0.5185. Okay. Now we wouldn't expect to get a very good answer only dividing it into 3 intervals. In fact, if you think back to the previous video where I had the diagram, we would expect to be overestimating it, right? If you picture those rectangles, they all overshot the curve by quite a bit. What's the right answer? Do we remember what the right answer is? The right answer is the integral of y equals x squared from 0 to 1. That should be 1/3. Well, 0.5 is not very close to 1/3. It's quite a bit bigger than 1/3. So we've overshot the right answer. But we also don't expect to get a very good answer only dividing it up into 3 rectangles. Let's run it again and divide it up into 10 rectangles. Now we get 0.385, still overshooting by a little, but getting closer to that 1/3. Let's do it in 50 divisions. And I apologize that this is, actually make this a little bigger this way so it doesn't cut it off like that. 0.3434, a little closer to 1/3. Let's do it with 100 divisions. The computed area of the rectangles is 0.3383. So to like 2 decimal places, about 1%, we are zeroing in on the right quote-unquote answer, the answer that we can derive using calculus. Let's keep going. Let's do 1,000 rectangles. 0.3338. So now we're down to 0.1% accuracy. Let's do 100,000. Oops, I think I'm going to... Let's run it again. I hit my 1 before it was done asking. 1, what did I say? We did 1,000. Let's do 100,000. So 1, 2, 3, 4, 5 zeros. 0.33338. So now we're down to close to 1 part in 100,000. Will it let me do 1,000,000? 1, 2, 3, 4, 5, 6 zeros. There we go, 0.3333338. So notice, as I make my rectangles smaller and smaller and smaller, our numerical calculation is getting closer and closer and closer to that mathematical calculation, which you said was equal to 1/3. Again, if you know how to do the calculus, you should be able to do that integral. If you don't know how to do the calculus, just trust me, the mathematicians know that the right answer to this question is 1/3. If we know the right answer to this question, why would we calculate the answer by adding up a bunch of rectangles? Can I, that didn't take very long. Can I do 100 million? 1, 2, 3, 4, 5, 6, 7, 8 zeros? Just testing how much code HS. Oh, not too bad. So how many decimals? 3, 3, 3, 1, 2, 3, 4, 5, 6, 7. We're down to better than 1 part in 10 million. Why would we do this if we can use calculus to find the answer? Because you can't always use calculus to find the answer because some functions are very complicated. Some functions are simply not integrable in any easy sort of way. And some functions would take as long to integrate by hand as it would to do this computation. Just to give an example of one such function, my PhD thesis involved calculating the scattering cross-section of one kind of particle off of another kind of particle. And when you do the calculation by hand to calculate this mathematical expression, the mathematical expression, I believe, was 50 pages long. So it was m squared equals, and then 50 pages of math. Imagine integrating a mathematical expression that was 50 pages long, written out by hand. Impossible, or nearly impossible. So that took about 6 months to calculate that expression, maybe less. It wasn't that long, maybe 4 months. And then how did I spend the next year and a half? I spent the next year and a half writing code like this to numerically integrate this expression, and it was actually a double integral, dx dy, to numerically integrate this expression to find a number, which was a point on the graph. And then I had to do that for every point on the graph to make a graph of this cross-section as a function of energy. So it was basically doing this, what we just did, for y equals x squared, for a function of x and y that took 50 pages to write down, and enough to make every point on a different graph, which is that area as a function of energy. This would have been, and I hate doing the math, has it been 30 years since I did my PhD dissertation? This would have been I started grad school in 92, so this would be like 94, 95, so yeah, 30 years. I wrote this program in C. I wrote it on Mac Plus, the little Macintoshes with the 9-inch screen that were like a little friendly box, a little beige box with a 9-inch screen. And the way I would run my code would be to set the energy, hit run, go home for the night, let it run for 5 or 6 hours, come back in the morning and get the number, save it to a file, then change the energy again and go home. So it would take 5 or 6 hours to run this double integral numerically, to approximate this integral. I recently, not super recently, when I started teaching computer science at RBC, so maybe like 5 years ago, decided to copy that program from my PhD thesis from the 90s and paste it into an online IDE like Reddit. And the program that used to take 5 or 6 hours to run ran in about 30 seconds on a modern computer. That is an example of what's called Moore's Law, which is that the processing speed of computers doubles roughly every 2.5 years. So you can calculate how many doublings there have been since the mid-1990s, and see if that works out from 5 hours down to about 30 seconds. So it's a very powerful method to do in 30 seconds of numerical calculation what would take probably weeks to do by hand. So numerical integration is a very powerful technique. There are many, many better algorithms than one we just did. Cutting the area into rectangles, you're always kind of overshooting the function by a lot. If instead you draw a line between your 2 points and all your shapes are like little trapezoids with a slanted top instead of a straight top, you converge on the answer much, much faster. You can take a whole course on how to do numerical calculations of complicated mathematical functions. I took a class as an undergrad called Numerical Analysis, which was just that. Not only calculating mathematical expressions using techniques like this, but also estimating your error. In other words, if I do this method with 100 million points, 100 million or 10 million points? 10 million points. About how close can I expect my answer to be to the right answer? In other words, there's ways to estimate how far each of these methods will be away from the real answer after a certain number of iterations. So it's a really, really interesting intellectual puzzle, and it's sort of a subfield of mathematics, numerical analysis, and writing these sorts of programs. So that's all I'll say right now about this method. Well, there might be one little video after this, but after we finish talking about this, I want to look at another way of finding the area underneath the curve, not by cutting it up into discrete shapes, but by randomly putting points in the interval and seeing whether they fall above or below the function, and then just adding up how many fall below the function. And if you do that enough times, like throwing darts at a dartboard, that will tell you how many of your darts landed underneath the curve will be an approximation of how much area is under that curve. That's called a Monte Carlo simulation, or Monte Carlo method, or Monte Carlo integration. We'll look at that idea in the next video, and then we'll go ahead and turn that idea into code.